Very good. Okay. So Kanav Setia has graciously, wonderfully volunteered to talk to us about variational quantum algorithms. He's the CEO of qBraid. He says he's in equal superposition of being an engineer and a physicist. I like that. I think that's clever. Anyway, Kanav, the floor is yours.
Perfect. There you go. Okay, can everybody see my screen?
I can.
Awesome. So first of all, thanks for inviting me. I'm delighted to be here. And I want to make this talk super interactive, so feel free to stop me anytime if you have any questions regarding anything. A little bit about myself. I'm originally from India, grew up there, did my bachelor's in aerospace engineering with a minor in astronomy and planetary sciences. Worked with the Indian Space Agency after completing my bachelor's at their facility called Semiconductor Laboratory. I worked on MEMS, design and development of MEMS, which are microelectromechanical systems. Sort of pitched Dartmouth College for a PhD in experimental physics because of that background. Got in, realized within the first year that I want to do theory, so ended up spending my PhD working on quantum algorithms for quantum chemistry problems. How do you take these atoms and molecules and try to understand them using quantum simulation on quantum computers? During my PhD, got to work with both the IBM and Google teams, contributed to open source software from both the companies for their quantum chemistry software. And eventually, towards the end of my PhD, realized that, hey, this might be a good time to start a company in this field. So ended up starting qBraid. So the way my talk is structured is I'm gonna walk everybody quickly through what we do at qBraid, uh, what the motivation was, and then we're gonna go jump into variation quantum algorithms. And the approach there would be starting from minimization of a function, what is variational principle? Um, what does it look like on a quantum computer? Why use quantum computer at all? And then it'll be hopefully free-flowing discussion. So qBraid is a one-stop platform for accessing quantum ecosystem. What quantum industries projected to grow up to over $1 trillion in value creation by 2035 by both projected both by McKinsey and BCG. And people think that it's going to produce a lot of value for various different sectors, including chemical, healthcare, finance, and logistics. And so if there's a lot of value to be created, and you really think about it, what are the key barriers to quantum adoption? It's actually limited expertise. There's fewer than 2,000 quantum computing experts in the entire world, which means the events like these and building community around these topics is incredibly important. Technology is quite complex. It takes a lot of time to understand this new paradigm of computing. And then ultimately, even when you understand it, it takes a bit of a time to make sense. Okay, you understand the technology, but how do you even use it to actually solve a problem that the world cares about? So all three are quite important. And this is where what we do is we provide the easiest access to quantum ecosystem. So there, besides the lot of difficult problems in quantum computing, there are some easy problems that people tend to spend enormous amount of time, which is like struggling with your normal sysadmin issues, cloud configurations in order to get access to these machines. So people end up spending way too much time jostling with pip installs, uh, making their perfect environment to run a quantum computing job on their local simulator or on a uh, quantum computer available through cloud. And so this is my bit of a personal story where I got access to both Rigetti and IBM devices in 2017 and 2018. And I remember spending over 500 to 1,000 hours just dealing with these uh, pesky issues related to Python. And Python is not even that hard. And ultimately, when it got to cloud configuration, that's something which was a new skill set that I had to pick up out of a necessity. I really didn't want to. So that's where we thought, okay, there might be a possibility of providing people a more streamlined access to a lot of these new resources. And that's essentially what qBraid is. We provide you a sandbox environment. It's basically built on Jupyter Lab, where you can just log in and get access to over 20 quantum computers and simulators. We provide you a lot of scalable CPUs and GPUs. And we've been maturing as a software integrator, as well as a place to do cutting edge research as well. I'll talk a little bit more about our work on uh, quantum software for healthcare, which is where we start from a protein and metal ion interaction that comes from a particular problem that happens to arise in Alzheimer's. And we have a pipeline built for studying these metal ion and protein interaction on a quantum computer. So our product consists of four main categories: qBraid Lab, SDK, qBook, and qBraid Runtime. Lab is the sandbox environment I was talking about, where we take you from not knowing much about quantum to running your first quantum program in under 10 minutes. And this is something that Professor Barry Bird has been using in his courses as well. Then we have qBraid SDK, which is state-of-the-art transpiler between different languages. For those of you who are familiar with quantum computing ecosystem, there's probably like, I don't know, over 50 companies that are building hardware. And most of them are also building their custom software stack. And so anytime you want to try out a new quantum computer that could be based on a different quantum computing architecture, you also end up having to learn their new software architecture or software. And that's the problem we wanted to solve with qBraid SDK. It allows you to start in any language of your choice and target any hardware. So if there's a mismatch between software and hardware, we transpile it on the fly and submit the jobs for you. Then we have qBook and Runtime, where the idea for qBook is it's a very nice learning platform that you can use to, we've got a whole bunch of different courses available. It works great on an iPad. It has a kernel attached, and you can use it to teach courses or roll out content to your learners, or you can take courses that we already have available. qBraid Runtime, as we were building the entire platform, we ended up building a decent amount of software infrastructure for backend software infrastructure to power our front end. And that's the part we're starting to open up to various quantum computing companies, where the idea is it's sort of like bring your own quantum computer, and we can just allow you to hook it up to the internet or to the cloud and open up access to the entire world. We'll provide you the job management, queue management, and all of that. qBraid Lab, as I mentioned, it's based on Jupyter Lab, and this is where I'll do my demo for variation quantum algorithms. For those of you who are interested in following along, you can make an account there. And then it has integration with over 20 different companies now, and you get access to pre-bundled over 50 Python environments, which are different versions of many different software, and almost every major provider that you can think of. Their software is definitely available on qBraid. We provide you things like easy job management, easy job submission, tracking various quantum computers, all from a single interface. This is the qBraid lab in action. You can see this is all your Python environments in one place. This is installing Amazon Braket, using which you can submit to all the Amazon devices. And then once you submit your job by running various different Python notebooks, those jobs show up on the sidebar, making it easier for you to track all the jobs and look at all the jobs that you've submitted in the past and understand their results, all from a very user-friendly, interactive environment. qBook, as I mentioned, it's something that works great even on mobile phones. It's basically a digital textbook. It is very interactive, contains video lectures, and we attach a kernel to the notebooks. Let's say, do qBraid labs quantum simulators approximately model the noise shape of a particular hardware? That's a good question. Yes, you can do that. The noise models are provided by actually various different companies, and many times we have not only simulators but emulators available, where if you submit a quantum job to a particular emulator, that emulator is basically simulator plus noise model, so it'll be very close to what you would expect on a real quantum computer. qBook, as I mentioned, it's a sort of a digital textbook with a whole bunch of different courses, and you can take multiple different courses, and many of these courses come with a lot of different quizzes for better understanding. And if you have a code snippet, we have a play button next to it. Just click play, the code runs. You can modify the code, click play again, run the code again. So it's meant to be sort of learn by doing approach. And the number of users have been growing consistently, and there's probably, I don't know, 10 to 20 professors in the fall who are very likely going to use qBook for their courses and rolling out their content. Yeah, as I mentioned, there's a lot of widgets for that you can include on your within your courses, and these are already something that are available on the many of the courses that we roll out. Then comes the last piece, which I said qBraid Runtime SDK or qBraid Ensemble. This name is something that honestly we're still debating on. So the idea here is as we built out the lot of the backend infrastructure that worked quite seamlessly with many of the HPC resources, GPUs, different CPUs, different kinds of quantum computers, different kinds of SDKs and input formats. So we had to build this sort of this orchestration software, which now we're starting to open up to various different quantum companies. Now, what they can do is they can provide, we give them a pre-made sort of this qBraid API that they can just extend. So we have very well-defined routes that a user would hit based on the front-end qBraid SDK. And we just tell the providers to extend them based on their quantum computers. And once they do that, their quantum computers goes online. And if they want to have access to GPUs, it is very naturally available from the same environment where they'll be extending their API. If they want to have access to an HPC resource, that's available as well. And all of those things get bundled and are made available to the front-end user. So when they submit a task, they can leverage not only quantum, but both classical and quantum resources. And all of this will be available from various different levels within the same software stack. So you as an end user will be able to hit different API endpoints to directly access the functions that API implements. Or you can just use qBraid SDK like you see here. From qBraid import get devices, get the status of the devices. All of the stack, as I mentioned, will have access to classical compute, and you'll also be able to access most of these resources not only from cloud, but also locally. So we recently launched qBraid extensions or Quantum Console for VS Code, Cursor, or Windsurf. For many of you who do most of your programming locally, you can just install qBraid extensions on VS Code, Cursor, Windsurf, and you'll have access to all of those resources from your local development environment. qBraid R&D, this is where we work with many of the enterprise customers like Airbus, Welcome Leap, and many others, where we focus on particular enterprise grade problems, such as like optimizing flight routes or figuring out how corrosion progresses in different kinds of materials, or the molecular level interactions that show up in Alzheimer's. And the platform has been gaining a lot of capability. Before I talk about that, there's a quick overview of the Alzheimer's pipeline that I was talking about. So there's this protein which has been known to play a crucial role in Alzheimer's called beta amyloid. And that protein shows up in plaque formation in the brains of patients with Alzheimer's. And people don't very well understand why and how these plaques are formed, but it is hypothesized that these protein molecules, beta amyloids, interact with metal ions, which triggers the clumping of the protein. And this interaction is something that we don't very well understand. And so here, what we propose is you can understand that interaction with this pipeline. What we do is we actually chop the protein into smaller pieces, and most of the protein is not that hard to understand and could be understood with just classical algorithms. There's only few pieces which is where the protein interacts with the metal ion that gets sent to the quantum pipeline. And within the quantum pipeline, we sort of follow the same ethos where we break up the larger system into smaller pieces using these quantum fragmentation techniques called quantum bootstrap embedding, local active space VQE, and then you run those on a quantum computer. You sort of stitch back the results together, and this is where we made like tremendous progress, and we'll be publishing many more papers in the coming months and / year. Our platform has been gaining a lot of popularity as well. We have over 19,000 users all over the world from over 120 countries, over 400 universities represented, and over 50 companies represented in our user base.
You got to add Drew to that list.
Absolutely. So how do we engage with various stakeholders, with enterprise clients? We have an entire workflow developed for the enterprise customers. Where we do some training programs, and we sort of come up with a area where you can potentially start doing a POC. With academics, it's very well established. A lot of our academic customers love getting access to various different quantum computers, qBraid SDK, for a lot of their courses and internal R&D. For quantum computing companies, as I mentioned, we provide access to qBraid runtime and Core qBraid Ensemble to hook up their quantum computers or simulators to qBraid platform. On the roadmap, it's basically we're developing a whole bunch of new stuff that would make it super easy for anybody to run workloads that include QPU, GPU, and CPU. I think that's pretty much it from my presentation. Happy to take any questions, and then we can jump into the demo part with focus on variational quantum algorithms.
So you mentioned, hello, there we are. Yeah, you mentioned transpilers from one language to another. And is there, my fellow Javateer, Johann Voss, has his own quantum computing book out with an SDK called Strange, written in Java for quantum computing. And I keep encouraging him, I keep trying to get him to make it so that he doesn't have to run on his own emulator, but can run it on various real quantum computers. Can qBraid play a part in this? Is there some role that the qBraid ecosystem can play to help him so that I can finally get him to do this for himself and for others?
I think so. We would want to understand. First, let me actually share the QR so you can take. Okay, so I'm gonna hold this up here. Yeah, I think so. What I would recommend is for your friend to take a look at qBraid repository. So github.com/qbraid/qbraid. It is open source, and you can understand how it works. And then there's a whole bunch of documentation, and it's very extensible. And the idea here is with an SDK, we have this transpiler where it's sort of this networked architecture where you can start from any node and end up on any other node. And all of these nodes represent quantum languages or quantum frameworks. So if you introduce one node, just one node and one edge to any of these programming languages, you automatically open up access to all the others.
Okay. So what he needs to do is build a node and connect it to, well, yeah, great. I'm gonna nag him about it
Perfect.
as soon as I can.
So is there an underlying language that defines a specific like abstract syntax tree for this network of transpiler connections? Or is each one of those edges its own program in itself?
The one in charge, why is it council with?
Sorry.
Sorry.
Yeah, so that's a good question. So one, the underlying language is Python that we use for the qBraid SDK. And then the underlying framework for these quantum languages is another separate layer to consider. For example, if your framework is written in a language that is not Python, then what you can do is you can have just one node to, let's say, OpenQASM3. And as soon as you have something that maps to OpenQASM3, then all the other languages get open. Or yeah, essentially, if, for example, if you're working in Java, then what you would want to do is just have a plugin within your framework to OpenQASM3.
And so OpenChasm is a fairly low level quantum language, so that I imagine all these nodes can upscale from that, right?
Absolutely.
Yeah, very cool.
And we have a question in the chat.
Let me take a look. What are your thoughts on different QC abstraction for algo modeling, such as tensor networks? So tensor networks are good, but they're approximations. So if you're looking to do a quantum-inspired approach in the near term using classical compute, then I believe tensor networks are very useful. But how much of improvement tensor networks provide for quantum circuits, I believe that's an active area of research. And that could be honestly very interesting, where using tensor networks to maybe do something to get more out of a quantum computer.
So Kanav, were you at qBraid's Year of Quantum event in Chicago a couple months back?
Yes.
I was there and I don't remember meeting you, so sorry I missed you.
That's okay. All right. Any other questions? Or should we move on to...
I want to hear about variational quantum computing.
Perfect.
Can't
So
wait.
awesome. So again, this demo is being done out of qBraid Lab. And so in my head, variational quantum algorithms are actually very simple. You've got some complex function of which you're trying to find a minimum. And now, before we even get to the quantumness of it, let's start with the very simple idea where you have this very simple function called f of x, and then you want to find, okay, where's the minimum of this function? And there are various ways to do this. It's a very standard approach. There's an amazing package called SciPy that is very popular, and people use it to optimize a whole bunch of various different functions. And you can just run this and it gets you the minimum.
Quick interruption. Are you able to zoom in one click here?
Okay, let me...
Much better. Thank you.
Oh, perfect. And so, as I was saying, very simple idea. What you're doing here is you have the function, and within the minimize, you just calculate the gradient, and you get to the minimum part. It's a very standard thing. How many people are actually familiar with this approach?
I'm familiar with the approach, but I really like it when my students don't use it and write some minimization algorithms themselves. That's just my special crazy thing.
Yeah, so that's how you get to learn, where you get to calculate the gradient yourself, implement various different approaches. Yep, Newton-Raphson, Runge-Kutta, various different orders of Runge-Kutta. So, and that's how you learn the behind the scenes of many of these minimization methods. And many times, you can also use many different methods that do not use any gradient approaches as well. Then there's another level where it's not a function, but rather function of function. You are dealing with sort of this open problem where you need a function of functions to get to the right solution. So for example, there's this very interesting sort of the first problem which led to this approach, which is where if you have this inclined plane and if you have 2 points, one is higher, one is lower, and you're looking for sort of this curve that takes the minimum time under the action of gravity, then what does that curve look like? And this is how the whole idea of variational principles involved. Now, you can imagine you have a straight line, but surprisingly, straight line doesn't take the minimum time. Then the other extreme would be you go straight down and then follow this path, but then that also doesn't take the minimum time. And then there's a specific path, which I forget what it's called. I think it's called cycloid, but definitely Google. And it's a very different curve that gets you the minimum time between these 2 points under the action of gravity. So the point being where you're not optimizing just for a minimum value of a function, you also have to find the function itself. So you have to parameterize, you have to come up with first a function of functions and use them to calculate the last value. So here we're dealing with sort of a given cost function, which is the sine, which is sine of x. Okay, and then you have a trial function, which is sine of x plus x pi minus x. And you can say, like, what's the point of this example? The point is just to demonstrate that you have a given function that you're trying to fit by a function of functions. And then you can calculate the difference between the 2 functions. This is where the cost function, it sort of gives you one single value that you can input in the minimization routine itself to get to the final value. Okay, and so you run this, and essentially you'll see that it's a weird curve. If you have, I think, sine x here, if you make this to be cos x, oh, wait a second. Yeah, okay, so sorry. That part actually worked just fine. So you have this target function sine x that you're trying to model with sine x plus x times pi minus x, and you'll see it gets modeled perfectly where you have blue line, which is the target sine x function, and then you have trial function. And another similar example where you have a simple rope, which is suspended under the action of gravity and held between 2 different points. And you're looking for the shape of the shape of the rope under gravity. And the way you would do it is you want to minimize the potential energy of the rope. Under gravity, if you just suspend anything, what it'll do is it'll try to minimize the total energy of the system. And here, because rope will not be moving, the kinetic energy will be 0. The only thing you'll have to take into account is the potential energy. And so you have, based on a given shape of the rope, I can give you any shape and you get to calculate the potential energy. So again, very similar idea where you have this function that takes into account the cable shape. And then for that cable shape, it calculates the potential energy of that shape, of the rope taking that shape. So now within that cable shape, you can have a functional, which is basically a function of function, and then you can run the minimization function on top of this potential energy and try to minimize it. And now you may ask, okay, how do I come up with this functional, which is a function of function? And that's where it's actually a bit of an art, where if you have some idea and you start with a good functional, you'll see you converge to very nice shape really quickly. But then again, I can just as well start with, let's say, different functional, and I don't end up remotely close to the correct shape. And so it is, as I mentioned, a bit of an art where you need to get a sense of what the actual function might be. But this could be mitigated. So for example, here, we were just starting with a single parameter and a single function. But if we make this single parameter to be a vector, and we start with both cos h and sin h, then you'll see I have a linear combination of these two things. And essentially, then I definitely end up with the right function in the end. So if you start with, as I mentioned, a linear combination of hyperbolic cosine and hyperbolic sine, then you can easily optimize around it. So even though you didn't have any idea, you can start with a bunch of different variations of different functionals and end up with this. So that's essentially a variational principle.
So if you don't start by using hyperbolic sine and hyperbolic cosine, but instead
You don't
start,
have to. You don't
right.
have to.
Can you, are there combinations of the kinds of guesses that will get you close versus a whole bunch of combinations of initial guesses that won't?
Absolutely. And so that's where you do need a little bit of the intuition. One good example is starting with like something called basis set. I'm not sure like how familiar people are here. Here are familiar with many of these concepts, but essentially you can start with like a long combination of sine functions with different frequencies. And essentially, it'll just be Fourier series, and you'll recover this function back. Does that make sense?
Yes, it does. Thank you.
Perfect. So here, the idea is you're starting with like a function of functions, and then you're trying to minimize an n cost function whose minimum you're looking for. And now there's this big question, okay, of like, how does quantum computers come into picture for a lot of these things? And in my head, it's a very simple idea. You can easily imagine a case where this potential energy function that we have here, imagine a very different function. And I'm telling you that calculating that function on a quantum computer is much easier compared to a classical computer. And if you ask like, okay, like what are the guarantees of that? That's something that I'm telling you. We can come back to asking this question whether there are functions that exist which are easy to calculate on a quantum computer and difficult on classical computer. But for now, if you assume that there are functions which are easier to calculate on a quantum computer than a classical computer, then the entire problem actually becomes a variational quantum, and the entire optimization routine that I just showed you, if you just replace this part with calculation of this part taking place on a quantum computer, then the whole routine is called variational quantum algorithm. And now there's a whole bunch of different flavors of like what exactly you're calculating on a quantum algorithm. And those show up as variational quantum eigensolver, where you're looking for literally the lowest eigenvalue of the entire matrix represented by a quantum circuit. Or there are many other problems where you're, again, looking for a minimum value of a complex optimization Hamiltonian. And if things made sense so far, we can go into, where is my introduction to quantum algorithms? Yeah.
Can I bug you to zoom in one click again? This
Absolutely.
stuff is very small over here. That's
Okay.
great. Thanks.
Perfect. So now
And
here,
I guess I'd like to butt in and just ask for a second. Which part of what you just said is the variational principle? You mentioned that in the previous page, the previous tab, and I understood what you were talking about, what you were saying, but I didn't get the idea of the principle.
yeah, so the variational principle is actually this idea of function of functions, which is called a functional, where you get to vary the functions to get to the to get to the minimum of a value which is represented by operating on these functionals.
Okay, thank you.
And do you do that as an iterative process, like a goal seeking type of thing, or?
Yeah, absolutely. So what you, coming back to the example that I gave, if you let's do this problem that I think I just covered. Minimize. Boom. Yeah. So this is the optimal cable shape problem where you have 2 points where one end of the cable is connected to this point, other end of the cable is connected to this other point, and all you're trying to do is trying to determine the shape of the cable. How does the cable look? And now, given any system, you might know this from introductory physics, where the system likes to be in a state of minimum energy. And so what you're gonna go after is a shape that reduces the total energy of the system. And if that's the case, the shape is not going to move, so the kinetic energy is zero. So the only thing you have to optimize for is the potential energy. So you need to make sure that whatever shape you choose, the potential energy needs to be minimum. Now, if that's the case, then you end up with a problem where you are basically not only throwing at the problem what the location of each point of the rope is in space, but rather the potential energy is determined by the location of each of the segment of the rope altogether, right? So then what the problem is, what sort of shape of the rope reduces the potential energy? And what you're going to have to do is throw at problem one by one different shapes of the rope to determine in general kinetic.
So if to make this a little more intuitive, if the rope isn't in the perfect shape for minimum energy, like at any point on this curve, the rope is higher or lower, then some sort of energy is keeping it higher or lower. And that's what you're trying to get rid of, right?
No, I think the idea is simple. Like, given the shape of the rope, I can calculate its potential energy, correct?
Right. But I mean, if you were to just kind of like draw a rope in here, you could calculate points where the energy to hold it up to higher than it should be would be a value, or energy to pull it down farther than it should be, right? I mean,
There's
is it okay?
no pulling down or pulling up.
Okay.
So it's actually very simple. Now imagine a rope was taking a different shape, or if I give you a different shape that you can test out. Okay, so you have rope. I can give you any shape corresponding to which you can calculate the potential energy. Correct? And we know
Yeah. Okay.
from we know that the rope is going to take the shape that leads to the lowest potential energy. So the problem becomes, what sort of shape has the lowest potential energy? And what you can do is you can imagine drawing different curves and calculating their potential energy one by one. And whichever curve has the lowest potential energy, you can say, okay, that is probably the most likely configuration that the rope's going to end up in. But then how do you go about testing a lot of these shapes and calculating their potential energy? That's essentially variational principle, where I come up with this strategy where I get to try out a whole bunch of different functions by using something called a functional, which is essentially function of functions. And then I get to calculate the potential energy of this functional and vary the parameters in such a way that I end up with the right shape of the rope. Yeah, I think Dimitri mentioned you can use Euler-Lagrange equations, which I think, which is also a very valid method. Okay, moving, what happened here? Okay, moving on to the variational quantum algorithms. Here, as I mentioned, the idea is simple, where what you do is you have a function that you're trying to, whose lowest eigenvalue is something that you're trying to calculate. And okay, how many people here have some amount of quantum algorithm knowledge? I'm trying to figure out how much of detail should I be going into. Okay,
How
so
will we gauge that from people? Um, uh, why don't people put number 1 to 5 in the chat? 1 being absolute beginner and 5 being know-it-alls.
that's okay. Okay, there's 1, 3, 3, 4, 4. Nice. Okay, there's a whole bunch of ones. Okay, so the idea here is what I'm doing here. It's a think of it as just a function, or just a matrix. Actually, matrix is a right way to think about it. And what we are looking to do here is we're looking to calculate the minimum eigenvalue of this matrix. And these are something which are called operators in quantum computing. And calculating these things with two IIs, which is basically a 2-qubit operator with identity, and then you have IZ, which is again 2-qubit operator. So now calculating these expectation value requires just 2 qubits. And whereas in classical computers, you require 4x4 matrix. So if I do something different and do X here, Y here, and then let's say just for the demo purposes, I add 4 qubit operators, then you have something that could be calculated using 4 qubits, but the matrix representation that a classical computer would need to use to calculate anything related to this matrix is going to be 16 by 16. And due to this scaling, you can imagine if I have a sort of, I call this something I call this thing Hamiltonian, which is again a bit of a jargon, but if I have a Hamiltonian represented by 50 qubits, you can imagine that I'll be dealing with a matrix size of 2 raised to power 50 by 2 raised to power 50. Okay, and that is incredibly hard to calculate with on a classical computer. Whereas, again, coming back to quantum computer, I'll be able to calculate different functions using just 50 qubits. And this sort of like hints at why there are certain functions that could be calculated much faster on a quantum computer than a classical computer. So assuming that there are functions, then the idea becomes very simple, where you have this function, and then what you do is, where's my ansatz? Yeah, so what you do is you create your ansatz here. So first, you have this Hamiltonian, and I can calculate the exact eigenvalue like so. And here, okay, I'm gonna go back to using just 2 qubits because my ansatz configured for 2 qubits. So here I have number of qubits in the system 2. And now because I'm only dealing with 2 qubits, I have 4x4 matrix representing those 2-qubit Hamiltonian. And 4x4 matrix is relatively easy to diagonalize. So I have the reference value, which is the minimum eigenvalue corresponding to this Hamiltonian. Then the next step that I do is I use a 2 local ansatz, which is, again, a fancy way of constructing that function or functions of functions that we talked about in the earlier stage. And then there's a bit of more, I would say, tools that take these functions and Hamiltonian and get you the minimum value corresponding to a function. So there's actually one-to-one mapping similar to what we discussed earlier. So let's look at this problem of cable shape, where I have this potential energy and then this cable shape. Now, in this new example that we were looking at, where did it go? Yeah, in this new example, that potential energy, think of it as being represented by this Hamiltonian matrix. That cable shape is being represented by this 2 local ansatz, where two local ansatz is your metaphorical shape. You take those two things and you do some more quantum mechanical operations to get to the final value of the potential energy. And that VQE is very similar to your minimized function that we were calling in the SciPy routine. And then essentially, if you run this, you'll see that where did it go? That you end up with the right minimum energy. And this graph basically prints the energy value as it converges. Okay, so far, any questions? I know.
I just want to check my understanding.
Yeah.
So two local is the model that we are trying to fit in order to approximate the Hamiltonian given, right?
No, so Hamiltonian is a matrix. So if you're looking for the lowest eigenvalue of the matrix, you need sort of like an eigenvector corresponding to the lowest eigenvalue. So if I can come up with the lowest eigenvector, then I can easily calculate the lowest eigenvalue. So two local is how we get to the lowest eigenvector.
Isn't two local parameterized a parameterized circuit?
Absolutely. Two local is a parameterized circuit that gets me the eigenvector. Or sort of like a vector that I can optimize. So two local ansatz, if I look at it, I get a state vector, which is again parameterized. So it's a vector that is parameterized that I can just feed into my optimizer to get to the lowest eigenvector.
Okay, so it's like the machine learning model in this case, right? We're just optimizing for the parameters of the two local model.
This whole thing is actually generalized quite well in quantum machine learning as well. Like if you start doing quantum machine learning, if you understood what I just explained, it's just a little bit more complicated, but the same basic idea. Where what you will be doing in quantum machine learning is figuring out, okay, I have this problem, then how do I come up with a Hamiltonian that represents my cost function?
Question? Can you give us a little bit more intuition about the magic that's going on in that two local call?
Absolutely. So two local, let's do it. So two local on Tron, let's see if that works. Oh, ansatz, I call it ansatz. Yeah, so two local is basically just parameterized gates on two qubits. So first, let's say.
I see that when you draw it, it's not giving you the details.
I can do it. Decompose. Oops. Yeah, there you go. So what you're basically doing is just applying one qubit gates followed by entangling them through CNOTs. Again, rotations on single qubits on all of the qubits followed by entanglement using CNOTs. And then what you can do is actually specify not only rotation blocks, entanglement blocks, but also repetition. Yeah. So if I do just 1 reps, then you'll see this is shorter. Yeah. So this is just 1 repetition where I have rotation, rotation, C naught, rotation, rotation. Whereas if I do 2, then you'll see that I have now rotation, rotation, C naught, rotation, 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 C naught, rotation, rotation. So it just repeats the circuit twice. Now, why would you want to repeat the circuit twice? Repeating the circuit twice, 3 times, 4 times would just mean you have more parameters in your circuit. That means you can play, you can explore much broader landscape. So again, a lot of what you might have learned in machine learning carries over quite nicely. So it's like an interplay where while you're trying to minimize a Hamiltonian or sort of a cost function, you will be playing with, okay, not only 2 local, but I could be using different ansatz, which is called, for example, there's another one, which is SU2, SU4 or SU2, I forget.
So in that circuit that was drawn, those single qubit gates that are in the circuit that drew, those are specified by those poly matrices in that original.
Sorry, can you say that again?
So in the circuit that you just drew, it shows single qubit gates.
Yeah.
And are those defined by those poly matrices that are in that's the big thing at the top you had that's
No.
building? No?
They are defined by these rotation blocks.
Okay.
So the entanglement blocks tell you, so what you again, oops, what you're trying to do is, this is your sort of matrix. So this Pauli summation of Pauli objects is essentially allowing you to define your cost function.
Okay. So this is building a state matrix that you're trying to optimize at that after. Okay.
Yeah. And so this is the matrix, and this 2 local ansatz is your parametrized ansatz or parametrized vector.
Okay. Got it. Thanks.
And then you vary those parameters and you end up with the optimized circuit. So for example, if you want to look at, so this is the parameterized one, but then I think I can do something like assign parameters dot. So, and then where's my EQE result dot, okay, I got result dot optimal parameters. So notice that this is all parameterized, this is thetas, and now what I'm doing is I'm assigning those parameters, and if I run this, you'll see the right parameters binded to this quantum circuit that got me this value. Okay, Qiskit, efficient SU2. Thank you. That's the one that I was looking for. Yes, so efficient SU2 is another one that you can use. Then if you're dealing with chemistry problems, chemistry is where I think VQE really shines, because a lot of the quantum chemistry knowledge surprisingly generalizes quite well to quantum computing realm. A lot of the knowledge base that quantum chemistry people had, computational quantum chemistry people had over the past decades, you can come up with like sort of these quantum computing representations. So a lot of the ansatz they already explored over the past 4 or 5 decades. You can actually come up with qubit operator representation, which then you can use as ansatz to optimize your Hamiltonian. Can we get a different circuit? Absolutely, you can. I think Michael just posted. That should be super helpful. Let me just show a quick demo of that. So what I can do here is you can see here I have 2 local. I can do efficient SU2. And then once I have efficient SU2, I can just copy this block. What? Okay, let's see. This is my same Hamiltonian. 2 local, I'm gonna need efficient SU2. And then I have 2 local here, so I'm gonna comment this block out and then represent it with efficient SU2. And then how do I specify qubit? No. 2. Okay, I think that should work. Okay, it seems to be going through. So efficient SU2 is a bit more convoluted. I forget what it used to do. Let's actually just pull it up. Efficient SU2 Qiskit. So, okay, so you have more rotations and then more entanglement. No, this is too local. Rx, Ry. Oh, yes, I think I remember it now. So in 2 local, most of the rotations were just RZ. So whereas in draw, whereas in efficient SU2, you have both Rx and Ry rotations. So the way I can check it is decompose reps equal to 1 dot draw. Yeah, so notice this difference. Let's bring this here. SU2 to local. So now I'm going to do ansatz SU2 dot decompose reps 1 dot. Okay, then I just need ansatz meow dot decompose. Zero reps. Let's grab this here. This thing. What? Oh, that's so cool. What?
This is the law of demos. Something has to go wrong for every live demo.
That's so cool, but like I'm not changing anything. This was working just fine, right? So if I do this,
It's a
And
little
if you,
grep.
if you don't believe Barry, just ask Bill Gates.
oh, I don't think, okay. Oh, I see. Okay, no. I got it. No, actually, I don't. And anyway, so the main thing that I was trying to show here, let's take a quick look. Maybe this is the only way to do it. So one, we're gonna do this, then this prints and decompose one. Okay, so notice that in toLocal, I specify rotation blocks. I can specify RY, RZ, RX, whatever I want. And then what happens is this is just RY gates followed by CZ, RY gates followed by CZ, and so on. Whereas if I choose SU2 and then run it, then you'll see that it incorporates both RY and RZ. And so that's the big difference. So you're not rotating around just one axis, but you're rotating around two axes. That's the big difference between efficient SU2 and toLocal. All right, I think that's pretty much it from my end, but happy to answer any questions.
I have a question a bit out of left field. The variational approach kind of brings to mind the Feynman path integral formulation of quantum mechanics. And the question is really I haven't really seen this put to work much. When looking at literature, I see it sometimes informing algorithms, or there's one algorithm informed by it for open quantum system simulations on quantum computing. I'm just wondering, are you aware of any practical use of the path integral formulation to find quantum algorithms for variational approaches?
Sorry, I didn't fully. I think your voice is not super clear.
Maybe I can just type it out in the chat.
Okay, that would be super helpful.
I
Thank
think
you.
with your voice closer to the microphone, it may be more clear. It was just a little muffled, but it got better when you just responded. So if you could just say it again.
Yeah, I have this headset, so I think my headset is acting up a bit.
No worries.
But I think
it's about.
Say again what your question is.
Yeah, I'm just wondering if you are aware of any algorithms that are informed by Feynman's path integral approach, because the interesting thing with that is that it essentially is the same kind of variational principle, but applied to the Lagrange function rather than the Hamiltonian. And it seems to me that there's a connection here between that formulation of quantum mechanics that is basically based on this variational principle and quantum variational algorithms. And I've seen some examples in literature, but there's really not a whole lot. So I'm just wondering if you know any other work that may connect these two concepts.
I think I've come across some of it, but I can't recall. I'm gonna have to look. But that's a good question. But I think the reason perhaps Hamiltonian is a bit more natural, even in case of variational approaches, is it shows up in Schrodinger's equation and dictates how the system's going to evolve.
Yeah,
And
Hamiltonian certainly dominates even adiabatic quantum computing.
so essentially, your system's doing something, like qubits are doing something, and they are evolving around under Hamiltonian. And I think then moving to a Lagrange would probably require, Lagrangian probably requires another transformation, which is going to be an overhead.
Yeah, I thought that it would be probably more natural for adiabatic quantum computing, but again, I don't really see anything in the literature about it. So yeah, I was just curious if you've seen anything.
Are you talking about path integrals?
Path integrals, yes.
Yeah,
It
these
seems
are
to be a natural
used in
fit,
quantum
right?
field theory to simulate systems with infinite degrees of freedom, like fields, which is in quantum computing, we're really using discrete degrees of freedom. So it's probably overkill to use such an approach. I mean, if I'm thinking about it naively, I don't really know how it would be applied to quantum computers.
It probably would imply something like a trotterization. Again, yeah, I was just curious because I've seen one paper, but only one paper really that did use that approach. And again, it was for open quantum systems simulated on quantum computers.
Wait, sorry, you said trotterization? How does trotterization come in?
Well, I just use it as a shorthand basically for, as you said, you have an infinite quantum Hilbert space really when you talk about path integrals. So you would have to do the same thing as you would do for calculations in QED, which you would put on a grid and basically have to discretize it.
Interesting. Okay, I'm not sure if I entirely follow, but certainly happy to talk later.
Yeah, no, it was just, as I said, out of left field. I was just wondering to see if you may have come across it. Thank you.
Absolutely.
So in the beginning, you mentioned quantum computers are good at solving optimization problems. Would the frameworks that are available at qBraid include QBO and variations of that for constraint-based optimization problems?
Sorry, I didn't catch that. Can you say that again, please?
So you were mentioned quantum computers being good at solving optimization problems. So my question was, are there libraries within the qBraid framework that do things like QBO or variations of it, or other constraint-based optimizations?
So I think like our goal is to provide access to various libraries. So we don't natively support QBO, but I do believe, I think you can use Qiskit to explore QBO problems, and even they have certain machine learning algorithm frameworks that you can use. And I don't think, like I said, quantum computers are useful for optimization. I think there's like a lot of promise there, but I don't think it could be said conclusively that they're going to be better.
Oh, okay, thanks.
Other questions? Well, I have one more. I have in the past tried taking some RY gates, some RZ gates, thrown them together, thrown together some entanglements, and tried to see if it would be a circuit that would find the minimum, do an optimization. And in general, the results that I get from a random combination of rotations and entanglements is garbage. So the question is, what is it about these particular ansatz, two local and SU2, that make them have a secret sauce for doing optimizations?
I don't think there's any secret sauce. They fail actually terribly at many of the problems. So especially like in chemistry, so two local and SU2 tend to work very well for, I don't know, up to 4 or 5 qubit systems because they're not that big. The number of parameters that you can tweak, you can almost reach, I don't know, any different vector through certain number of gate operations on a quantum computer. But as the problem size grows, so when you're dealing with, let's say, 10 to 20 qubit systems, if you have a Hamiltonian from chemistry, two local and SU2 fail terribly. And even in case of, I would say, optimization problems, I don't have a good intuition why they would succeed.
Okay.
Because especially two local, it's very restrictive in it's very restrictive in the in the kind of gate itself. So you're going to be exploring very small section of the Hilbert space in the first place.
Okay. Any other questions? Any other comments? There being none, I want to thank profusely our speaker, Kanav Setia, today for coming and talking to us about variational quantum algorithms. And to wrap it up, Ron, do you have anything to say about our Chicago Quantum and Beyond group before we break?
Yeah, I'd also like to thank our speaker for a very interesting presentation. It's good to get back to stuff. I mean, I haven't done any coding like this for about 2 years, so it was a great refresher to get back into what's available out there. So thank you so much. And hopefully we'll be able to convince you to come back with some other topics sometimes in the future if you're available.
Yeah, absolutely.
Yeah.
Should we spend a minute or two on George and Victor's questions in the chat?
So George, naive chemistry question. I honestly think I'm actually curious. Why do you think 6 or 12 qubits would simulate benzene?
Well, order of magnitude, I'm not sure of the exact number, but in nature, the benzene solves this variational problem. In the same way, like a soap bubble classically solves a very difficult minimization surface problem given an arbitrary curve dipped into the soap film, which is actually very difficult mathematically or computationally to do.
Okay. So if we're talking about such approaches, then it could be doable. I mean, like you can potentially start with benzene, come up with like a local active space that's only 6 to 12 qubits. And if you truncate it well, you might be able to get good results. But the whole problem around many of these quantum chemistry approaches is to be able to do for most physical systems, right? Like they're actually quite large systems, which could easily be represented by I don't know, 5 to 10 qubits. But then that becomes an output more of your art than like a scientific structured approach.
Thank you. And also just, I want to thank you in general for your very clear explanations and demo, which help me in my mind connect the classical mathematics to the quantum formalism. So I really appreciate that. Thank you.
Thank you. Thank you. Very kind words. Glad to hear that. Hamiltonian representation. Any reference material for Hamiltonian representation in quantum algorithm? I'm not too sure if I completely understand what was you trying to say here. Reference material for Hamiltonian representation in quantum algorithm? Are you saying like Hamiltonian from quantum mechanics representation in quantum algorithms, or representing a general mathematical function in terms of qubit operators? Gates versus ion-based quantum computers. Ion-based quantum computers also have gates. As a standard software developer with no other background, I was considering the quantum field. Good idea? Is individual study better, or would pursuing masters? That's a good question. I would say going to school helps, mostly because it forces you to be disciplined. Otherwise, if you can be disciplined and study all of these things on your own, there's actually no requirement of paying a lot of hefty fees to universities.
I like those
Yeah.
hefty. They pay my salary.
Absolutely.
If you're just starting out in quantum, I can highly recommend that you make sure you're up to speed on linear algebra and complex numbers. And there's some people that say you don't really need all that stuff to know how to program quantum computers, but from my standpoint, it really helps a lot to be able to know what those underlying structures look like.
Definitely. There are different levels of involvement in quantum computing and different aspects. There's the physics, the engineering, the algorithms. There are all kinds of ways of butting your nose into the field. Some of them require less academic preparation, and others require more. I think that's the general sense. Okay, now that everybody's asked more questions, after my big finish speech, I'm going to do my big finish speech again. Kanav, thank you so much for this presentation. We are definitely going to try to have you back, and I will nag you relentlessly until we do get a commitment from you to come back. And in the meantime, everybody who's on our meetup page, watch out for our next meetup. It's going to be in July. We will see you then.
Thank you. Bye.